Hi everyone, this is Miss Moore and today we are learning about kinetic and potential energy. And yes, there will be math in today's lesson, so you need a calculator. Please pause the video here while you go find a proper scientific calculator, not the one on your phone. Okay, so you may recall from our last lesson that kinetic energy is the energy of motion and potential energy is the energy stored by an object as a result of its position, shape, or condition. So in today's lesson, we will be focusing primarily on gravitational potential energy. Here are some warm-up questions to get you in the zone. Number one, a person stands very still at the edge of a cliff. What type of energy do they have and how do you know? Number two, where did the energy come from that allowed this person to do work on themselves to reach the top of the cliff? And number three, if the person put on their parachute and stepped off the edge of the cliff, what types of energy would they have? Please pause the video here while you think through all of these questions. Okay, let's compare our answers. For question one, we should say that the person has gravitational potential energy, which we will abbreviate as GPE, because they're above the surface of the planet. And they're standing very still, so they don't have any kinetic energy. Technically, they have trace amounts of other energy because they're a living being. So there's chemical potential energy stored in their muscles, and there's thermal energy involved with regulatory body functions. But the big form of energy that they have, if you were to tabulate all of it, would be gravitational potential energy as the winner. Anything that could fall has GPE. So where did the energy come from that allowed this person to climb up the cliff? This energy came from the chemical potential energy stored in their muscles, which in turn came from the food that they ate, which all traces back to plants eventually, which get all of their energy from the sun, which is electromagnetic energy. And finally, if they put on a parachute and stepped off the edge of the cliff, they would be in motion, so they would have kinetic energy, but during the falling process, they'd still be above Earth's surface, so they would have gravitational potential energy all the way until they hit the ground. And once they hit the ground, there's no more gravitational potential energy. Okay, let's move on to today's lesson where we can explore kinetic and potential energy in more detail. Starting with a recap from last time when we discussed mechanical energy, you may recall that objects can have multiple forms of energy at the same time. For example, an object can be in motion, meaning it has kinetic energy, but it can also be storing various forms of energy, potential energy, simultaneously. And the sum of all of this kinetic and potential energy is the mechanical energy of the object. The formula that we had for this last time was mechanical energy equals kinetic energy plus potential energy. So how do we calculate kinetic energy? Any object in motion has kinetic energy. But how much kinetic energy it has depends on two things: its mass and how quickly it's going, its speed. Here's our formula for the kinetic energy of an object. EK equals 1/2 mv squared. This tiny little k next to the e is called a subscript. A subscript is attached to a variable and is part of that variable. So it's not e times k, it's ek. You may also hear it referred to as e sub k, like e subscript k. That is our variable for kinetic energy. So kinetic energy, or ek, is measured in joules, which we abbreviate with the unit symbol J. M represents the mass of the object, which is measured in kilograms, which we abbreviate as kg, both lowercase. And v is the speed of the object measured in meters per second, which we abbreviate as m/s for meters per second. I'm going to highlight this formula because it's really important, as are all of the quantity and unit definitions. All of these units belong to a family of units called SI units, which stands for Système International, which is the international system of accepted units for measuring quantities pretty much everywhere except in the United States because they use the imperial system of measurement. So joules is the SI unit for energy, kilograms is the SI unit for mass, and meters per second is the SI unit for speed. So whenever we're performing calculations with these formulas we're going to be learning today, your quantities have to be in these units. If they're not, you have to convert them. What do I mean by quantity? All of these are quantities. It's important to understand the difference between a quantity and a unit. So let me give you an example you're more familiar with. If I told you that the distance from one side of our classroom to the other is 20 meters, distance is the quantity and meters is the unit of measurement. We always use symbols for our quantities, like we've outlined here, EK, M, and V, and likewise, we have symbols for our units, J, kg, and m/s for meters per second. You need to be familiar with each. So how do we calculate gravitational potential energy? Recall that potential energy is the energy stored by an object as a result of its position, shape, or condition. And the three main types of potential energy are gravitational, elastic, and chemical. In Physics 10, we are only performing calculations with gravitational potential energy, and we are literally going to say gravitational potential energy so many times in the coming weeks that we can just abbreviate it GPE and refer to it as GPE. So how do we calculate this? Well, it also depends on an object's mass as well as its height above the surface of the planet that it's on and the gravitational acceleration of the planet that it's on. You may have heard gravitational acceleration just referred to as gravity, which is fine. That means the same thing. So here's our formula for gravitational potential energy. EP equals mass times gravitational acceleration times height above Earth's surface, where EP is measured in joules, just the same as EK, which is abbreviated with the symbol J. M is the mass measured in kilograms, just like we did above. H is the height above the planet's surface measured in meters, which is the SI unit for length or distance, abbreviated with little m. And g is the gravitational acceleration measured in an interesting unit, meters per second squared, which has the symbol m/s squared. That is the SI unit for acceleration, which we're going to explore more in Physics 11. But basically, when you think about how quickly something is accelerating, you're thinking about how fast it's speeding up. Or likewise, if an object is decelerating, you're thinking about how fast it's slowing down. So fun fact, where do these units come from? Meters per second is the unit for speed. So if you want to know the rate at which something is speeding up or slowing down, you have to take meters per second per second. Now, what many people don't know is that units behave the same way as numbers when you perform algebra on them. So if we divide m per second divided by seconds, it's kind of like if we had, I'll just give you another little example over here. It's kind of like if we had 3/4 divided by 5. We just use the same rules that we would use for dividing fractions. 3/4 is the fraction in the numerator times the reciprocal of the denominator times 5/1. Reciprocated becomes 1/5. So it's the same thing here. Meters per second times, what's the reciprocal of seconds? S/1 becomes 1/s, and now we have m/s squared. Hence all the algebra that we did at the beginning of the unit so that we are not scared of these sorts of operations. That's just fun facts, though. You don't need to truly understand that till Physics 11, so I'm going to erase that, which I'm sure is a relief to some of us. So if I just go back up to where we were talking about gravitational potential energy, I'm going to highlight for those of you taking notes without the lesson template. This formula is very important, and all of these units and quantities. Again, these are the quantities. And these are the SI units. Every planet has a different gravitational acceleration based on the mass of that planet itself. So we can say every planet has a unique acceleration due to gravity or gravitational acceleration at its surface. On Earth, g is approximated as 9.81 meters per second squared on average. It's slightly different if you go somewhere that's really, really high above sea level, like Mount Everest, and it's slightly different again if you go somewhere significantly below Earth's surface, like you dig a very, very deep hole. So let's do some examples to practice our new formulas. Example 1, a tennis player holds a 0.2 kilogram tennis ball stationary in the air just before serving it. If the ball is held 1.2 meters above the ground, determine the kinetic energy and GPE of the tennis ball to the nearest joule. So there is a way of solving physics problems which may seem overly complex to you right now because these are the easiest physics problems ever. But physics problems become progressively more intense in terms of the quantities that you're working with and the formulas that you're working with. Even over the course of the unit, they will be becoming more complex, let alone what you're going to encounter next year in Physics 11. So the system of how to solve a physics question that I'm going to show you now is a skill, okay, which practicing now is only going to make your life easier if you take senior physics. So the first thing that we do is we list all of the things that we know from the question, and we list the things that we know using the quantity and the unit. So it says the tennis player holds a 0.2 kilogram tennis ball. What kind of quantity is that? Is that the speed? Is that the height above the ground? No, it's the mass. What is our quantity symbol for mass? Little m. So we're going to make a list at the side of the problem for all the quantities given to us in the question. Little m equals 0.20 kilograms. It also says that the ball is held stationary before it's served. What does it mean for something to be stationary? Stationary means not moving, which means that the kinetic energy is 0, which further means that the speed must be 0. So v equals 0. What else do we know? The ball is held 1.2 meters above the ground. This is the height. H equals 1.2 meters. That's it for things that we know. Now we're ready to start solving. The first step in solving is to write down the formula that we are supposed to use to find the answer that we need. We're told that we need to find the kinetic energy. So I'm going to make a little list here of the things we're supposed to find using the correct symbols. What is the symbol for kinetic energy? It's E sub k, or EK. We're also supposed to find the gravitational potential energy. What's the symbol for that quantity? EP. Now that we know what we're looking for, we can choose the correct formulas. The formula for kinetic energy is EK equals 1/2 times mass times speed squared. Once you've written down the formula, you can substitute in the numbers for each quantity. EK equals 1/2 times 0.20 kilograms times 0 meters per second squared. Now you can go ahead and type this into your calculator, or you can just recall that multiplying any number by 0 is just going to make it equal 0. So our kinetic energy is 0 joules. This is our final answer, so I'm going to put a little box around it. I'm also going to move this over a little bit so that we have space for potential energy. Okay, what's our formula for potential energy? EP equals mass times gravitational acceleration times height. Let's substitute in the numbers that we know. The mass is 0.20 kilograms. And now I'm running out of space because of my picture of the tennis player. It's okay, I'll curve upwards. G is 9.81 meters per second squared, and H is 1.2 meters above the ground. You can go ahead and multiply all of these numbers together in your calculator, and you will get 2 joules. I'm going to put a box around that because it's my final answer. Okay, please try example 2 with the volleyball player on your own and pause the video here while you do it. Okay, let's compare our answers. Hopefully you listed all of the quantities that the question gives us on the side and identified the quantity that we were supposed to be looking for as well before you started solving. Keep in mind that the question also tells you how to round your final answer, and it did for the previous example as well. It wanted the kinetic energy to the nearest joule, which means that we need to round to the nearest ones position in our final answer. So I got 9 joules for part A, and in part B, when we were looking for gravitational potential energy, I got 4.4 joules because now we're rounding to the nearest tenth of a joule. And in part C, we have to recall the formula for mechanical energy, which is the sum of the kinetic and potential energy. And they also said to the nearest joule, which means we're rounding to the nearest ones position. Okay, let's move on to the next example. Example 3, a 3.4 kilogram rock falls off the edge of a cliff. When the rock is 11 meters away from the ground, it's falling at a speed of 2.5 meters per second. I would like you to please try part A using the same skills that we just practiced in example 2, and then wait for me when you get to part B because I would like to show you how to solve this type of problem. Pause the video here while you do part A. Okay, let's compare our answers. Hopefully you started by listing all the quantities given in the question and itemizing what we were supposed to find, which was mechanical energy in this case, which is simply the sum of the kinetic energy, which we can calculate, and the potential energy, which we can calculate. And then we can find the sum of those two values and round our answer to the nearest joule, and I got 377 joules. So how is part B different? Part B says if a rock has 500 joules of kinetic energy right before it hits the ground, how fast is it falling to the nearest meter per second? What this question is saying is that as the rock falls towards the ground, it has both kinetic and potential energy, and then right before it hits the ground, H is pretty much 0, so the rock has a maximum amount of kinetic energy. In this case, the kinetic energy is 500 joules. And we're supposed to find how fast it's falling, which is the speed. Symbol for speed is v. So how do we solve a question like this? Well, We only know two formulas so far. We know potential energy equals mass times gravity times height, and we know kinetic energy equals 1/2 times mass times speed squared. We pick the formula that contains the quantity that we need. So the potential energy formula will not be helpful to us here. We need to use the kinetic energy formula. Then comes the algebra part. We need to rearrange this equation and isolate V before we substitute in the numbers. Let's go through that process together. EK equals 1/2 times mass times speed squared. We're going to systematically undo all the operations that prevent V from being by itself, starting with the 1/2, which we can undo by multiplying each side of the equation by 2. Let me show you why this works. 1/2 times 2 is the same as 1/2 times 2 over 1. When we multiply fractions, we do numerator times numerator and denominator times denominator. So we end up with 2 over 2, which simplifies to 1. When we multiply by 2, it's canceling out the 1/2 at the front of the equation. So now we have 2 times EK equals m times v squared. What separates the m and the v? Multiplication. So how do we undo the fact that we have times m? We have to divide each side by m, because m divided by m is just 1. M cancels out. Now what do we have? 2 times EK over m equals v squared. We're not finished yet because we have to get rid of this squared. How do we undo a squared? We take the square root. If we take the square root of this side, we have to take the square root of this side as well. So now our new formula is v equals the square root of 2 times EK over m. Now we're ready to put our values in. V equals 2 times 500 joules divided by the mass, which is 3.4 kilograms. So how to put something like this in your calculator? If you have a proper scientific calculator, when you hit the square root button, it'll give you an option to put a bracket around the operation that you're doing on the inside. And if you don't, well, you're going to have to work out 2 times 500 first, and then divide that by 3.4, and then take the square root of your answer. On a calculator, you actually need to add a second set of brackets around the numerator so that it goes 2 times 500 and then takes that whole answer and divides it by 3.4. So on your calculator, you need an extra set of brackets here. Okay, calculate away, and you should get 17 meters per second. Okay, please try example 4 on your own, which is very similar to what we just did, to practice this new skill of rearranging equations and solving for speed. Pause the video here while you try it, and then we'll compare answers. Okay, here's my answer. We were asked to round to the nearest tenth of a meter, so I got 54.8 meters per second. All right, example 5, the last one of today's class. A basketball player throws a 0.63 kilogram basketball up in the air. At the peak of its flight, the basketball has 35 joules of GPE. How high above the ground is the basketball to the nearest tenth of a meter? I'm going to solve this through with you guys just to get a little more guided practice on the algebra, but you can also try this on your own instead of following along with us. So let's list the things that we know. The mass of the basketball is 0.63 kilograms. At the peak of its flight, it has 35 joules of GPE. So EP equals 35 joules. How high above the ground is the basketball? This means we're supposed to find the height above the ground, h. We know two formulas. EK equals 1/2 mv squared, and EP equals m times g times h. Which one contains h? That's the one we're going to use, not the kinetic energy formula. Just like in the last two examples that we tried, the variable that we want, h, is not by itself, so we need to isolate h algebraically. EP equals m times g times h. To undo this, we can do it actually in a single step. If we divide each side by m times g, then the m's cancel out and the g's cancel out. So we're left with EP over mg equals h. Now we can go ahead and put our numbers in. H equals 35 joules divided by 0.63 kilograms times 9.81 meters per second squared. So the basketball is 5.7 meters above the ground. Please don't forget to round to the nearest tenth as the question asked us to. Okay, I know this was a really intense lesson today with a lot of algebra. I feel that you just need to get some practice and you'll be able to develop some confidence with these skills, okay? It's going to be okay. So please go ahead now and complete assignment 2, which will be due next class. Bye for now.